Hello everyone, good morning. I'm audible, right? Okay, so this is lecture number 3 of modern algebra. So if you haven't watched the previous two classes, so go through all the previous videos, right? I think the board is class. Just a minute. Okay, so we'll start. This is lecture number 3 of modern algebra. So if you haven't watched the previous two classes, so go through all the previous videos, right? Okay. So in the last two lectures, we have introduced the definition of group, and then we have seen almost 25 examples. And then we have solved around 5 problems, right? So they will give a set, they will give a binary operation. We need to check whether it forms a group or not. So this is what we have discussed in the previous class. So I think in the previous problem, we have solved 5 problems in the previous class. So in this class, what we will do is we will be solving 4 more problems. They will give a set. And then they will give binary operation. You need to check whether it forms a group or not. So we'll do 4 more problems based on that. After that, we will be introducing definition of order of an element, right? We'll be introducing definition of order of an element, and then we'll be seeing some theorems. See, groups and order of an element. These two are single topic, right? So when you are studying, you combine these two topic, that is groups and order of a group, order of an element, right? Order of an element. So in this class, we will be doing 4 more problems. We will be introducing definition of order of an element, and then we'll be doing some theorems also, right? Okay. So we will start with problem number 6. Show that the set of all 4 matrices, set of all 4 matrices forms a group, forms a group with matrix multiplication. So 1 0 0 1 minus 1 0 0 1 0 minus 1. So we need to tell that this forms a group under matrix multiplication, right? Under matrix multiplication. So again, very simple. It's a finite group with 4 elements. So you just form a K-list table. Let us call this element to be I. Let us call this element to be A. Let us call this element to be B. Let us call this element to be equal to C. Right? First make a K-list table and then work it out. Very simple. So the operation is normal matrix multiplication, right? It is a normal matrix multiplication. Just a minute. Adjust the board. Hello. Hello. I think it will be audible now, right? Sorry. Is it clear now, right? Okay. So I don't know where the audio is stuck. See, we are just performing a matrix multiplication, right? So B, and so on. So we have filled the Cayley's table. So they have shown, we need to show that these four matrices forms a group with respect to matrix multiplication. They have given four matrices. I'm just naming this as I, A, B, C and forming a Cayley's table. So if you want to perform A, B, it is a normal matrix multiplication only. So you need to check the all four properties. So it will be closed, it will be associative. You need to apply definition, right? I'm just putting it here, but in exam point of view, for A comma B belongs to G, A star B will be also in G. See, here the star is matrix multiplication, and we know matrix multiplication is always commuted associative. Matrix multiplication always associative, always associative. And what about existence of identity? Existence of identity. So there is a matrix I which is 1001 in this set is an ID element. And what about inverse? So since it is an finite, you need to find inverse for each element. So what about inverse of I? It is I. And what about inverse of A? Inverse of A is A, inverse of B is B. All the elements are self-inverse. See, this is also an group that satisfies Klein 4 group property, right? This is also a group that satisfies the property of Klein 4 group, right? So this is the problem number 6. Is it clear? Everything is clear, right? Audio and video. Everything is clear, right? Okay. So we'll move on to problem number 7. So what is the set of all matrices of the form? So that the set of all matrices of the form, of all matrices of the form x, 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 and this x belongs to R star, right? R star is non-zero real number, a group. So we need to show that it forms a group. So here you can see we have all 2 by 2 matrix with all the entries are same, right? With all the entries are same. So we need to show it forms a group. See, this is okay. So we will prove this. This is an R star. So non-zero real number, right? All real numbers except zero. Okay. So first we need to show it is closed. This is an infinite set, right? This is an infinite set, but in the previous problem it is finite set, but this is infinite set. So you take any two element in G, right? So let A comma B belongs to G. Here every element is a matrix, 2 by 2 matrix with all entries are same. Let us take X to be X, 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 X. Let us take B to be Y, 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 Y. Right? So the what about AB? This A star B here is AB. The group with respect to matrix multiplication, right? With respect to matrix multiplication. See, the operation is very important. Okay. So what about AB? So it is X, 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 X. y, 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 y. This will be x, y, x, y. So it will be 2xy, 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 2xy. And you can see this also, all entries are same, right? All entries are same. It will be in G. So G consists of all those 2 by 2 matrix, full all entries are same. This also all entries are same, so it is closed. So for associative, so let us take three matrix. Let us take A, comma B, comma C belongs to G. So let us take A to be X, 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 B to be Y, 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 C to be some Z, 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 Z. So what about A star, B star C, A star B, star C? So A star, so what about B star C? It will be 2YZ, 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 2YZ. A star B is 2XY, 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 2XY. Star C, C is Z, 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 Z. See, you can do this, right? So we will have 4XYZ, 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 4XYZ. So it will be same only, right? So if you do this, we will have 2XYZ plus 2XYZ. So all entries will be 4XYZ here. Here also all entries will be 4XYZ here. So this will be associative, right? And what about the identity? The existence of identity. So for A belongs to G, there exists some element E in G such that A into E has to be A again. So let us take A to be X, 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 X. We don't know what is E. Let us take E to be E, E, E. So here every element is a matrix, right? 2 by 2 matrix with all entries are same. So that means I'm taking E to be a 2 by 2 matrix. Now we need to find E. So we will have 2xe, 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 2xe is equal to x, 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 x. To compare these two elements, so that means we will have 2xe is equal to x. That means E is equal to 1 by 2. So we have E to be equal to 1 by 2, 1 by 2, 1 by 2, 1 by 2. The ID element. The ID element, right? So you can check it out if you take any 2 by 2 matrix with same entries, you operate with this, you'll be getting that same element again. And inverse, the existence of inverse. So for A belongs to G, there exists an element A inverse in G such that A into A inverse has to give me an ID element. Let us take A to be X, 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 X. Let us take inverse to be some A inverse, A inverse, A inverse, A inverse. You can take anything, right? Is equal to E. So 1 by 2, 1 by 2, 1 by 2, 1 by 2. So we will have XA inverse, XA inverse. So we will have 2 XA inverse is equal to 1 by 2. Right? So you just have you will have a 2 by 2 matrix here and compare the first element and compare the first element. I think I'm having to with the camera. Just a minute.